Hi and welcome back. This is video 3 of lecture 2 for University Physics 2. In the previous two videos, we discussed temperature, the different systems of units that you see used for it, and we worked some problems dealing with heating, primarily how you see a change in temperature in some cases, and in some cases you see phase transformations. What I'd like to do today is to talk about something called heat transport. So we know that heat flows from things that have high temperatures into things that have low temperatures. Port. Now, that said, there are three basic methods that you see heat use in order to go from point A to point B in space. The first method is called conduction. Now, conduction is heat transport via contact. So, for example, if you take a pot of water and you put it directly onto, say, an electric burner, the heat flows from the burner into the pot primarily due to the fact that it's in contact with it. If you take your hand and you reach out and you grab a glass of cold water, the heat goes from your hand into the water via contact. Now, the second method that you see is called convection. Now, convection is a special case of diffusion in that it requires gravity to work. So this is basically heat transport via the movement of fluids. Now, by fluids, I mean a liquid or a gas. We're going to talk individually about these here in a moment. The third method, and the most common method that you see nature transport heat around, is via radiation. Now, here, when we talk about radiation, we're talking about heat transport via light. For example, if you go outside on a sunny day, you'll notice that if you put your back to the sunlight and you're wearing something dark, your back will get warm. That is heat from the sun being transported to you via light, and you're receiving it and getting some of it. So let's talk about these individually. Now, to begin with, we're going to talk about conduction. What I'd like to talk about initially is how it works. So if you think of two objects that have different temperatures. So here's object 1, it's a solid. Here's object 2. Let me just sort of fill in some of these little atoms in here. Now I'm going to draw the springs. Actually, I'll tell you what, let me draw a boundary. Whoops, I don't want to use a big thick line like that. Let's use this one right here. I'll draw a boundary like this. This is where object 1 is. And this right here we'll say is object 2. So this is number 1. This is number 2. Now let's pretend that object 1 has a lower temperature. I'll call it T sub C in comparison to, say, object 2. So when you bring them into contact, really what's happening is at the interface here, at the boundary, between these two objects, what you're letting happen are the atoms and molecules in this one and the atoms and molecules in this one interact. So if you think of this right here sort of as being that boundary, then as the atoms and molecules here vibrate back and forth, let me just sort of draw some guys right here. So this is 1, this is 2. As these vibrate back and forth and these vibrate back and forth, at this interface they interact with each other. They collide, if you want to think of it like that. So what happens is because these have more kinetic energy than these do, there is a bulk flow of energy from the right side to the left side. Now remember, these are connected to each other via bonds that look like springs, and those bonds extend back, out into their neighbors back over here. So what happens is heat flows from the right side of this to the left side gradually, and it flows into this one right here, such that each particle on both sides ends up with the same average kinetic energy. Okay, so these guys are vibrating back and forth, and these guys are vibrating back and forth, such that there's no benefit for energy transport between the two. Which means that what's happened here is the temperature here, Tc, has gone up, Th has gone down, and you've equalized temperature. Okay, so it's this flow of energy, really, is what the flow of heat is in this case. Okay, and in all cases, basically. All right, now, so from a more practical standpoint, if you think of and this is more applicable, to things separated by a material. So if you think of having a material here, and we have two regions of space, I'll call this 1 and this 2. And maybe you have a high temperature here and you have a low temperature here. What keeps the temperatures sort of in their own space would be this material that's separating the two. Now, this material here has a thickness that I'll call D, and it has an area which I'll call A. All right. Now we know heat is going to want to flow through from this side to this side, and over time, what you expect is the temperature in region 1 to go down and the temperature in region 2 to go up. So you could talk about the power that's being lost from region 1 and into region 2. But it has to traverse this material right here, whatever this is that's separating the two. So now power is really just, how the heat is changing with respect to time. Okay? And if you think about it, it's going to be proportional to the area. Okay? So the more area that you have here in this material, the more area there is for the atoms and molecules, we'll say in this room, to interact with this and deposit energy into. And if you look at the relationship between the power loss and how much area you have here, it ends up actually being a linear relationship. Now, another thing that this is proportional to is 1 over the thickness of the material. The thicker the material, the less power loss. Okay? Think of it like wearing a shirt versus a thick coat whenever you go outside on a cold day. Okay? So in a situation like this, for a big D, overall this is small. All right? So it's an inverse relationship. And if you actually do, if you look at this empirically, if you test it, you'll discover that there's an inverse relationship here. So this is an empirical statement. Now, it's also proportional to the change in temperature. The bigger the change in temperature, the more kinetic energy on one side that you have in comparison to the other. So the energy loss is actually faster. Okay? Now, if you put all this together, what you'll discover is that the power loss is proportional to the area of the thing, the change in temperature that you're looking at, and also, the inverse of the distance between the two. Now we put a constant out in front. This is a coefficient of thermal conductivity, okay, called K. And if you look at the units are watts times meters over meters squared times degrees Celsius, or watts per meter degree Celsius. Okay? Now, typically, what happens here is that since you're going from a high temperature, like your initial temperature is greater than your final temperature, this delta T ends up being a negative. So a lot of times what's done is a minus sign is put in front to denote the fact that your power overall is a positive number, and then you add in the direction later on. Now, that said, there's another way that you can write this, more of an instantaneous view, and that is you put the minus sign in front to show the fact that delta T is negative in general, and you write it as minus K times A times dt dx. dx being the thickness here, and dt being the difference in temperature. Okay? Now, which one you use, depends upon the situation. I actually prefer using this one right here, but 6 of one, half a dozen of the other. Because if you're dealing with discrete temperature differences and discrete thicknesses, you can just promote dt and dx to being discrete. Okay? Now, so as an example, what I like to look at is how much power is lost through a glass window that's 1 meter by 1.5 meters and 2 millimeters thick. I'm going to assume that the inside temperature of the room that has the window is 70 degrees Fahrenheit, and that the outside temperature is 35 degrees Fahrenheit. Now, I also want to know that if I leave the heat on inside the room, maintaining a constant temperature of 70 degrees Fahrenheit and therefore a constant loss of power, how much that's going to cost me. Okay? So what we're given here is a thickness, D, of 2.00 millimeters, which if you put this in meters is 0.00200 meters. We have a length that's 1 meters and a width that is 1.5 meters. So the area here, which is length times width, would be 1.50 meters times 1 meter, which is going to be 1.50 square meters. Okay? Now, the temperature inside the room is the high temperature. That's T sub H. That's 70.0 degrees Fahrenheit. Now, if you convert that to degrees Celsius, it ends up being about 21.1 degrees Celsius. That 1 is repeating, and I'm going to use that in my calculation. On the outside, it's 35.0 degrees Fahrenheit, which, if you convert that again to Celsius, is about 1.67 degrees Celsius. Again, this is repeating. Now, let's see here. It's a glass window. If you look up the thermal conductivity coefficient for glass, it ends up being about 0.84 watts per meter degree Celsius. Now, likewise, we're given that the power company that we're dealing with to maintain this room for 2 hours which we're going to assume that 2 is exact just to sort of fiddle with the math a little bit here. 2 hours, there's 3,600 seconds in an hour, so that's 7,200 seconds. Okay? We're assuming that this is dollars per joule is actually what this is. I'm going to show you how this works. Is 96.04 dollars for every 1,000 kilowatts hours. Now let's go ahead and convert this real quick. A kilowatt hour is 1,000 watts times an hour. Now, a watt, if you think about it, is a joule second, and we're multiplying that by 1 hour. As I said earlier, there are 3,600 seconds for every hour. So what that does is to allow us to turn this into joules. So a kilowatt hour is 3.6 times 10 to the 6 joules. Okay? So that means that if we just go ahead and plug that conversion in there. Let me do this here. It's 96.04. That's your dollars. 1 kilowatt hour is 3.6 times 10 to the 6 joules. And then I have to divide that by 1,000. So this is approximately that doesn't look right. Oh, the kilowatt hour is in the denominator. It's 96.04 per 1,000 kilowatt hours. Sorry about that. It's like that doesn't make sense. So we need to divide by 3.6 times 10 to the 6 joules. So that's going to be 96.04 divided by 1,000 times 3.6 times 10 to the 6 joules. That's better. So basically, this is going to be about 2.668 times 10 to the minus 8 dollars per joule. Okay? So, now we've got all our conversions and everything else done here. Let me clear this just so I can have a work area. And we're trying to find a few things. Like I said, initially we want to find the power loss, P. Then we want to find the cost. Now, we're maintaining this for 2 hours, so I'm just going to say cost like that. All right. So, again, the power that you're looking at here is going to be K times A times delta T over D. Our K here is 0.84 times 0.84 watts per meter degree Celsius. The area is 1.50 square meters. The difference in temperature is TH minus TC. That's going to be 21.1 degrees Celsius minus 1.67. Actually, what am I saying? It's actually TC minus TH, final minus initial. Final is 1.67 degrees Celsius minus 21.1 degrees Celsius. That's where your negative is. And now we're going to divide this by D, and D is 0.00200 meters. So if you plug this in, it's 0.84 times 1.5 times 1.67 minus 21.1. Then I'm going to divide that by 0.00200. Okay, so I get here that you're losing about 12,240.9 watts. Okay? That's how many joules per second are exiting the room. So, what's the power loss? It's this right here. 3 sig figs here. Basically, everything here ends up being 3 sig figs. So if I round this to the correct number of significant digits, it's going to be about this many watts right here. There's your loss. Now, so the heat's going to be on for 2 hours, maintaining a constant temperature, which means our power is going to be constant as it goes. Now, power, remember, is energy over time. So the energy that would be lost would be power times time, or would be, and I'm going to use the positive value of this just because we're looking at the total amount of energy that's being lost. Now remember, 2 hours here is 7,200 seconds. So you end up with a total of 88,134,480 watts lost. Now, I want to take this to get the cost and multiply it by my conversion from dollars to joules, because and that actually shouldn't be watts, that should be joules. I'm sorry, we lost that. Okay, so 2.668 times 10 to the minus 10th, or 10 to the minus 8th rather, dollars per joule. So if I store this, and then we're going to take that and multiply that by 2.668 times 10 to the minus 8th. I get it's going to cost us to heat this room just for 2 hours about $2.35. So now, so that's conduction. Let's talk convection now. Now, we're not going to be doing any math with convection, but it is an incredibly important method of heat transport, and we'll be talking about it again at some point later on. So the way to think about convection is this. So I want you to think about having a pot of water on a stove. So here's my water, like this, okay? And so what's going to happen here is I'm going to heat from below this pot of water. Now initially you have your little atoms and molecules just sort of hanging out in here doing their thing, right? As I heat this pot of water, the pot itself, remember, is made out of metal. It's a solid, and the atoms and molecules in it are going to move back and forth with the temperature of whatever it is they're getting from the heat down here below. Now, if I were to zoom in and look very closely at the bottom of this pot and then look at some of these water molecules that are doing their thing like this, right? So as one of these water molecules comes in and hits the bottom of the pot, Remember, at the bottom, this is the atoms and molecules make this pot up are vibrating. So what happens is that it kicks it off. Okay? So it kicks it off, and that water molecule leaves with more kinetic energy than what it had before, which means it has a higher temperature. So you have this flow upwards like this of water molecules. Now, however, what's keeping this water in the pot is gravity. And that's the critical thing here with convection, is that you have gravity present. Okay? So gravity is acting here, pulling down on all this. So as your water molecules flow up like this, what happens is they push the ones up here down. As they flow up, you have this flow of hot material up pushing cooler material down. And you end up with loops like this. Convection loops is what we call them. So if you've ever cooked with a convection oven, inside the oven what's happening is it's moving air around, trying to maintain a constant uniform temperature throughout the oven. Okay? Now convection only works if your atoms and molecules are able to move around like this. So convection is only good in fluids. That is, liquids or gases. Now, on the other hand, if we go back here to conduction, conduction requires that the atoms and molecules in here be in place. And at the boundary, that's where you have your heat transport. Solids. Solids are the only things that do that. So conduction works in solids. Convection itself works in gases and liquids. Now, that said, let's talk about the third type. Now, the third type of heat transport is radiation. Now, so you know that I have that I derive things in this class, and in an effort to show you where they came from, because there's there's intuition that you can form when you get a hang for you get a hang of deriving this stuff. You get a better understanding of how nature works. The unfortunate truth of the matter is that the law that describes how radiation transports energy depends upon a number of things. It depends on an understanding of electricity and magnetism, because that's what makes up light. You're going to find out. It also depends upon an understanding of the quantum nature of light. Now, there is a law that when you put these things together and you turn the crank and you add in the study of thermodynamics, that will allow you to show the relationship between the power radiated and also the temperature of the thing that's doing the radiation. It's called the Stefan-Boltzmann law, and it looks like this. You okay? All right. So the next one we're going to talk about is radiation. Now, you know how I like to derive things in this class. Unfortunately, this particular law, which is called the Stefan-Boltzmann law, depends upon an understanding of electricity and magnetism, and also an understanding of quantum mechanics. When you put these two together and then you stir in a little bit of thermodynamics, what you end up with is a law that shows how light transports radiation based off of temperature. Now, so the law looks like this. Is sigma A epsilon T to the fourth. Okay, this is the Stefan-Boltzmann law. Okay, now this constant right here is the Stefan-Boltzmann constant. It has a value of 5.67 times 10 to the minus 8th joules per, or actually let me write it this way instead of joules per second, watts per meters squared Kelvin to the fourth. This is a weird one. Now in this one, you absolutely have to put in your temperature as Kelvin. Okay? This law was arrived at after we formed a good understanding as to what temperature is, and it requires that the temperature that you're dealing with here not have any negatives. There must be a zero. Okay? Now, so, I'm a zero at the bottom. The lowest temperature is zero. So, Stefan-Boltzmann law, like I said. Now, what this means here is that any material, now this particular law works for solids, liquids, and gases. All states of matter. No matter what the temperature that they have, will radiate energy. Okay? Anything in nature that has a temperature radiates energy away as radiation. And that's the reason why I said that this is the preferred method that nature uses. This is the most common way that you see heat transported from one point to another point in space. And that's because, as best as we can tell, everything in nature has a temperature. Okay. Now, typically what we're looking for is the difference between the power being radiated by something and the power already present due to the things around it that are radiating. So the way to think about this is that, you know, like I had mentioned earlier, if you go outside and you have a black shirt on, radiation hits your back from the sun and you feel warm. If you have something that puts out radiation, any radiation that falls onto it is going to add to its internal heat. So when you're looking at the actual amount of energy being radiated, what you want is the difference between what it's putting out and what's falling onto it. That tells you how much in truth it's actually losing. Okay. Now, let's talk about what this epsilon thing here is. Now, epsilon is called emissivity. Now, an emissivity of 1 is a perfect emitter and receiver. Receiver. There you go. Okay, so a good example of a perfect emitter and receiver would be the sun. These things also have a name. They're called black bodies. They're called black bodies because light that falls onto them is 100% absorbed, which means they don't reflect light. And if something doesn't reflect or scatter light, it has the color of true black. Now, you have emissivities of 0, which do not exist, because that would be an object in nature that has a temperature and doesn't emit. Okay? So your emissivity sits somewhere between a little bit above 0 and 1. Now, as an example of this law, in this example right here, we have a CPU, which is the brains, if you want to think of it, of a computer. And CPUs actually generate a lot of heat whenever they run because they're filled with electrical circuitry that has what's called resistance to it. It generates a lot of thermal energy. We'll actually be talking about that as we go further through the course. So anyway, to get rid of the heat, what they do is they bolt on top of a CPU a thing called a heat sink. Now a heat sink is usually aluminum or something like that, and it has fins on it right here. And what the fins do is they allow you to create a lot of surface area without having a whole lot of volume, which means that you can get rid of a lot of thermal energy into the environment through radiation, but you don't have this enormous thing sitting on the inside of your computer that's just nothing but a flat disk of area or something like that. So they get their area by having multiple fins. Now, so in this case, our CPU has 10 fins, each of which has an area on one side of 5 centimeters. So a true area, discounting the edges here, would be this side plus this side. That's for one fin. Now, the heat sink itself is made out of oxidized aluminum, and it has an emissivity of 0.4. So the question here is, what's the radiated power? Now we're going to assume that the CPU itself needs to stay around 40 degrees Celsius, and the environment itself has a temperature of 20 degrees Celsius. So what we've been given here is the following. So the area of one fin, which I'll just call, well actually it's just the area of this one side of one fin, which I'll call A1, is 5.0 centimeters squared. Now we have 10 fins and each fin has two sides. So the total area that's going to be emitting radiation, two sides to 10 fins, each of which has an area of A1. Okay, so 2 times 10 is 20, 20 times 5 is 100. So this is 100 square centimeters of area that's capable of emitting this. Now we need to convert this to square meters because, you know, obviously we work in the MKS system and we'll be doing that here in a moment. So next we have aluminum. Now the emissivity of aluminum is 0.4, at least of the oxidized stuff. We know the initial temperature, or at least the temperature, we'll call it TH. It is 40 degrees Celsius, that's our processor's temperature. And the air and the environment around it has a temperature of 20 degrees Celsius. Now, we're trying to find the emitted power, okay? But remember, like I had said back over here, what happens is you have the radiation that's being emitted by the thing that has temperature, and then you have the environment dumping heat into the thing that's emitting. So the true radiated power is the difference between those two. So our Stefan-Boltzmann law looks like sigma epsilon area T to the fourth. The difference in power that we're looking at, which I'll call P average here, is going to be the hot stuff minus the cold stuff, which would be sigma epsilon A T sub H to the fourth minus sigma epsilon A T sub C to the fourth, or just sigma epsilon A TH to the fourth minus TC to the fourth. Now, we have to convert, because we work in Kelvin, these temperatures to Kelvin, and we also, again, have to convert this to square meters. So let's go ahead and do the area in square meters first. So here, it's 100 centimeters squared. We know that for every 1 meter, there are 100 centimeters. And you have to do that conversion twice. You do it once, and this becomes a 1 You do it again, and it's 1 over 100. So our area is 1 over 100 meters square, and I'm not going to bother putting that into decimal form. Now, so remember, when you convert from Celsius to Kelvin, what you do is you add 273 to it. So 40 plus 273 is going to be 313 Kelvin, right? Because 273 Kelvin plus 40 Kelvin, 313 Kelvin. Now, this one right here is 273 Kelvin plus 20. So 293. All right. So let's go ahead and figure out what our average power emission is. So sigma, remember, is Stefan-Boltzmann law, the Stefan-Boltzmann constant right here. So let's just go ahead and snag that. We'll paste it here. So sigma, 5.67 times 10 to the minus 8th watts per meter squared, Kelvin to the 4th. Epsilon, that's the emissivity, 0.4. We don't need this anymore, so let me ditch it. The area, 1 over 100 meters squared. And then we have our temperature difference, which is going to be 313 Kelvin to the 4th power minus 293 Kelvin to the 4th power. So let's plug this into the calculator. Let's see here. 5.67 times 10 to the minus 8th power times 0.4 times 1/100th times 313 raised to the 4th power minus 293 raised to the 4th power. So the power emission in this particular case is getting ahead of myself there. 0.505 watts. So half a watt, which is not bad. Now, in truth, these things will get hot enough almost to melt. Like they will shut themselves down because there's so much heat energy present. So, if I wanted to keep this in sig figs, I have 2 here. I have 1 here, 1 here, 1 here. So this ends up being about half a watt. So there's your answer. Now, let me show you another way you can use the Stefan-Boltzmann law. So the sun itself puts out a lot of energy. It radiates 3.828 times 10 to the minus 6 watts, or 10 to the 26 power, rather, watts of energy. Now, how do we know that? Well, if you remember our section on waves and stuff like that, if you capture through intensity, some radiation coming from something like the sun, and you know how far away something is, you can figure out how much power that thing is putting out. So just by noting the intensity, say at the orbit here at the Earth, we can, and knowing how far away the sun is, we can determine how much power that the sun puts out, overall. So this is something that we know. Now, the emissivity of the sun is 1, and that's because the sun is a black body. Now, black bodies absorb 100% of the energy that fall onto them, and they also emit 100% of the energy that they have. Okay, so um, actually, let's redo that. Okay, so um, do that again. So in this example, we have the sun, which radiates 3.828 times 10 to the 26 watts of energy. Now, we know this because if you remember our conversation about intensity, um, if I can measure the intensity of the sunlight, say at the Earth's orbit, and I know how far away the sun is from the Earth, I can tell you how much power is being put out. So this is something that we can empirically measure. So we know it puts out this many watts, and the emissivity of the sun is 1. So the sun is a black body. Now, black bodies are called black bodies because, again, they absorb all radiant energy that falls onto them. And you see, when you see something, you see it due to the light that is either being emitted by it or is being reflected or scattered off of it. Okay, so with the sun, it does not reflect or scatter light, and that's because it absorbs all of it. So, for example, let's pretend that you look at somebody who has a red shirt. You see a red shirt. What's happening is light's falling onto that shirt, and that color that you see is what's being reflected or scattered off. In the case of clothing, typically it's scattering. Now, so what that means is if you absorb everything that falls onto you, you're black. That's the color that you have. So, that's the reason why they're called black bodies, is because, if you take away the energy that they're emitting, they would appear to be truly black. Now, so what I want to know is what its surface temperature is. We know its radius. It's 6.957 times 10 to the minus 8th meters. So we're given the power, which is 3.828 times 10 to the 26 watts. We're given the emissivity, which is 1. And we're given the radius of the sun, which is 6.957 times 10 to the 8th meters. Now, what are we trying to find? The temperature. Okay, so let's look at the Stefan-Boltzmann law real quick. So the Stefan-Boltzmann law says that the power that something puts out is equal to some constant times what type of emitter it is. Is it a black body? How much of a black body is it? Times the area that is doing the emitting times the temperature to the 4th power. So the area of the sun that's doing the emitting is its entire surface area. So in this case, the area is going to be 4 pi times r squared, and the r here would be the radius of the sun. We know the power, we know its emissivity, we know everything here now except for the temperature. So, the temperature here, if you solve for it, is going to be the power divided by sigma epsilon A to the 1/4 power. Okay? So that's 3.828 times 10 to the 26 watts divided by sigma, which again, 5.67 times 10 to the minus 8th. Watts per meter squared, Kelvin to the 4th. Epsilon's 1. And our area here is 4 pi times r squared. The r is 6.957 times 10 to the 8th meters. You got to square that. All this is being raised to the 1/4 power. So it's long, kind of ugly, but not too bad. So, let's see here. 3.828 times 10 to the 26 power. Oops. There we go. Going to divide that by 5.67 times 10 to the 8th power, or to the minus 8th power rather. Times 1 times 4 times pi times 6.957 times 10 to the 8th power. And you got to square that. All right. Syntax error. There we go. Let me raise that to the power of 1/4. I get 5,772 Kelvin. So, this is the temperature of the surface of the sun. I mean, that's what it is. We have multiple ways of determining it, and this is what it is right here. So, just looking again, at the intensity of radiation here at the Earth due to the sun, and knowing how far away the sun is, we can deduce what the power is, and knowing what the power is and what the radius of the sun is, we can easily figure out its surface temperature. Okay, so that's it for this chapter. In the next chapter, we're going to start to develop some of the microscopic aspects of thermodynamics, and I will see you then.